In today's substitution elimination pre-finals review, we're going to take it a step back and go into each of the reactions, SN1, SN2, E1, and E2, from the very beginning. Because you tend to learn the reactions, work on all the problems, and then forget the little details. I want to make sure that after today's session, you are solid, crystal clear with exactly what happens and what to look out for. I don't want you to worry about taking notes, anything that you see me writing. Just go ahead and sign up, the URL on the screen or in the video description below, and you will get a copy of today's session notes, a bonus practice worksheet, and a link to other recordings of live streams that I've done, so you can be as prepared as possible for your final exam. And with that, let's go ahead and jump into the SN2 reaction. The SN2 reaction, the name for each of the reactions, or the abbreviation for the reactions, is telling us exactly what that reaction is. S stands for substitution, N is nucleophilic, and the 2 doesn't tell us the number of steps because a lot of students do think it's the steps. The 2 tells us that it is bimolecular, and that just means how many molecules are reacting together at the same time. Substitution, nucleophilic, 2 molecules reacting at the same time. Let's see what that looks like with a mechanism that starts out like this, with a molecule that is a simple straight chain, a bromine sitting on a secondary carbon. It's on a wedge because this molecule is chiral. And I react it with something that looks like this, NaOH in DMSO. So let's talk about all the pieces and then go through the mechanism specifics itself. With substitution elimination reactions, we have to pay attention to if I have a carbocation intermediate or if I have stereochemistry that I have to pay attention to, because if there's no carbocation, the molecule itself, I want you to notice that you have the leaving group, that's the group that we're about to kick out, sitting on a secondary carbon. This chiral carbon right here is secondary. And this is important to recognize because when you do a direct attack, the less hindered the molecule, the faster the reaction. And so with a secondary leaving group, it's not going to be the fastest SN2 reaction, but it's fast enough that it can happen. What are we using to attack? We have the Na+. Anytime you see that in the front of something like an O or an N or a C, it's just a positive spectator to balance the fact that we have a negative ion right there, OH-. OH- is electronegative enough where it can hold that negative charge, but it's not very happy with that charge. That makes it reactive. That makes it want to attack something. DMSO is a solvent that you've probably not seen before getting into substitution elimination reactions. DMSO stands for dimethyl sulfoxide, and it looks like this. We have a sulfoxide, sulfur double bound to an oxygen, and on the sulfur we have 2 methyl groups. What is interesting and important with this solvent is that even though I have atoms that would typically give me polarity, the fact is the sulfur and oxygen are close in polarity, they're bound to each other. The hydrogens are sitting on carbon atoms, which are also close in polarity, or close in electronegativity, and therefore doesn't really have polarity. And so even though I can have some partially negative up here and partially positive here, this is not a polar enough molecule to stabilize charged intermediates. This is considered a polar aprotic solvent. Aprotic in that it does not have, a second, I seem to be getting feedback here. Okay. Aprotic in that it does not have any ability to do hydrogen bonding in solution. It's not very polar. It's not ideal for charged intermediates. I want you to pay attention to that because that is critical. And that is going to help us favor an SN2 reaction. The mechanism happens like this. I'll redraw the OH- right here. If the OH- wants to come in and attack, remember substitution, I'm going to substitute, I'm going to replace. But if it wants to come in and attack the carbon from the top, from the front face of the molecule, it can't because bromine is sitting right there and it's blocking. The only way that the OH- can attack is from the opposite side, from the bottom, from the back side of this molecule, creating a new bond to carbon. Now, why does it attack that carbon atom? Why even bother? We know that the OH minus is reactive, it's strong and negative. But what we also have to remember is something like bromine, which is a halogen. It's highly electronegative. It's pulling on the electron density between itself and carbon, pulling, making bromine very partially negative. Now, carbon, having the electron density from that bond pulled away, makes it very partially positive, and that is why the OH minus is attracted to the carbon. That is what drives the reaction. And when the OH minus attacks the carbon, carbon is going to have too many bonds. The bond between carbon and bromine is going to break. I mean, bromine was already pulling on those electrons anyway, so it's just a matter of completely grabbing it all and popping it off, which is going to result in a molecule that looks like this. The bromine already had 3 lone pairs. We showed these in orange over here. Now it has a negative charge. It's off somewhere in solution. We don't care about it. The OH minus came in from the bottom, behind the molecule, which we'll demonstrate with with dashes. And that is our final product. So you'll notice that we had a chiral molecule to begin with, bromine coming forward. We have a chiral molecule as the product, OH going back, and that's because with an SN2 reaction, we have an inversion of chirality. If at any point you have questions regarding anything I discussed, go ahead and type it into the comments. The first we have from Tula. Me and my friend are fully depending on you for studying for organic chemistry. Well, thank you so much. I am so honored that you're able to turn to my videos to help you, and hopefully this will help you with this topic as well, because this is the most difficult Orgo 1 topic and the second most difficult topic, in my opinion, in all of organic chemistry. Spectroscopy is the only one I consider harder. So this inversion of chirality, let's take a look at it with a smaller molecule so that you get a better idea. We'll take something like CH3Br. CH3Br, if I look at it from this weird angle, say I have a hydrogen here, a hydrogen here, and a hydrogen here. And then my leaving group, I know this is drawn a little bit off, but you can envision almost an upside down chiral molecule here. And bromine is my leaving group. We'll use the same OH minus, and we'll show the OH minus first, trying to attack in this direction. It can't. There's no way for it to reach carbon. And I know we're trying to show it here sneaking in, but the way this orbital is set up, you have the bonding going on here, the bonding orbital going on there. It can't sneak in there. It cannot reach. This is not going to work. Instead, it has to come in from this side. And because it's directly attacking the molecule, it attacks the partially positive carbon. And just think of it as it punches it so hard that bromine just gets kicked off by the force. And the way I imagine this is, just picture a bench and just pretend this is a park bench and there are people sitting on it. I'm not really sure how to draw sitting people, but here we go, sitting people. And then somebody comes in and just runs and then does a jump to sit down here so hard that, oh, hold on. I'm trying to see if I can get these people to move. No, it's not going to work. But what I was going to try to show you is if we have another person and they just imagine I have a toddler. And this kid is just no regard for anyone's personal space or safety. He will just catapult right on to wherever you are and get here with so much force that the blue person just gets pushed off. So imagine everyone just getting catapulted off the bench. Let me know if this example makes any sense in terms of understanding how the OH minus just gets in there, attacks the carbon, and that bromine gets kicked out. Because it's a one-step reaction, the bromine can't get kicked out in this direction because it is literally being shoved off the other side. And so for the final product here, the hydrogens that are facing up into and out of the page haven't changed. The hydrogen going down hasn't changed, but the O came in from completely the opposite direction, and that is how you have an inversion of chirality. Now, technically, this molecule is achiral because I have 3 hydrogens, but what I want you to focus on here is how it happened and why we have that inversion. So when you see something like this, that concept makes sense. If we look at all the players in this reaction, Notice that this entire reaction was one step. What is the rate determining step in a one-step reaction? Well, that was a trick question, because if there's only one step, that is the rate determining step. And so the rate of an SN2 reaction is going to depend on everything involved in that first step. Rate SN2 is equal to some constant K specific to this reaction times the concentration of both molecules, the alkyl halide and the nucleophile. So this is why we call it a bimolecular reaction. That's the 2 in SN2. Because of how the OH minus or the nucleophile in general is coming in, SN2 reaction can only happen if there is low steric hindrance. What type of molecules have low steric hindrance? And I'll just put the note here. The SN2 is going to require either a methyl, a primary, or a secondary carbon. SN2 cannot happen with a tertiary leaving group, and I forgot to label them before, but the carbon that is holding the leaving group is called the alpha carbon, and this right here, the group that gets kicked out, that is called the leaving group. And so no tertiary leaving group, meaning no leaving group that is sitting on a tertiary carbon. And we have a question. I'm just joining. How does the DMSO work? DMSO is just the solvent. This is the liquid that everything gets dissolved in. And because it is polar aprotic, it doesn't stabilize much, and it does not like to have any charges forming. That is why DMSO tends to work better in an SN2 reaction. So this is a polar aprotic solvent, as I have listed here, and it will prefer the SN2. It prefers a nucleophile. It does not like a base. All right, really good question. Hopefully that made sense. If you have any questions on SN2, go ahead and type it in. Let's talk about the nucleophile a bit more. The nucleophile in an SN2 reaction. I showed you that the way this reaction works, and I'll show you again with just the CH3 bound to a Br. And specifically, let's look at the carbon bound to the Br. We have the hydrogen, hydrogen, and another hydrogen. The way that this works is the bond between carbon and the leaving group is a polar bond. We talked about how bromine is partially negative and carbon is partially positive. What attracts the nucleophile to this carbon is the fact that it has a lone pair that is either partially charged or fully charged. Now, because the molecule is doing a direct attack, you'll typically see a negative charge, or you'll see a molecule that is polarizable. I don't know if polarizable is a word, but it's something that we can polarize. And so if you think about something like a carboxylate, we know from the acid-base chapter that a carboxylic acid is a pretty strong acid because when you deprotonate it, you have a negative charge on an oxygen that is able to resonate. That negative can resonate here, and that will give me another contributing resonance structure that looks like this now with the extra lone pair sitting over here, the negative charge on the upper oxygen, and then a new pi bond having formed over here. This distributes the charge and makes it a weak base because in a base you want to have a strong charge. If the charge is resonating, then it's not as concentrated on one atom, and that makes it not as desirable for this molecule to reach out and grab a hydrogen. But if we bring this resonating hybrid, so the way that you would picture the resonating hybrid intermediate, it looks something like that with a partially negative on both. If you bring this next to a positive charge, then all the negativity is now going to flow in this direction because it wants to get close to that positive. The negative and positive are attracted to each other, and this is what we mean by polarized. All of the negativity goes towards that spot where the positive is, goes towards this right here. And then when that negativity is all concentrated, it is able to attack the carbon. For this reason, if you have something with resonance that you can polarize, the resonance makes it a very weak base, but the ability to polarize makes it a very good nucleophile, even if it's technically a weak base. A couple of other common ones that you're going to see is, well, this one, the nitrile is not polarized, is not able to resonate because we only have 2 atoms here. But the fact that it has the pi bonds, that does allow it to shift the negativity here as needed. The azide anion, N3-, is another one because the N3- can be written with resonance like this. This is one resonance structure that has minus, plus, minus. But if you bring this next to a positive charge, it can also do something like this. Let's say we put a positive charge right here. Then everything will resonate towards that positive. So if I have the 3 nitrogens in a row, the negativity will all resonate here. And that will make it look something like, I'm trying to think, if I do like that, that should give it a minus 2. 1, 2, 3, 4, 5, 6, 7. 7 minus 5, yeah. Well, 5 minus 7 is negative 2. Then we would have a triple bond right here, like that. Okay. Formal charge is great when you're trying to figure out what's going on, because that is the fastest way that I find. Yeah, neutral, positive, negative 2. Do you see how all of the electrons just came to hang around this nitrogen so that it can be next to the positive, so that it can attack? That is why this is so important. All right, so the key things to recognize with an SN2 reaction, we already talked about the fact that it's bimolecular. We need to have a strong nucleophile. We cannot have a tertiary leaving group. We're going to have an inversion of chirality. Is there anything else that's important to know for an SN2 reaction? I think that covers it. So let's move on to the E2 reaction. What does the E2 reaction stand for? What is an E2 reaction? What is not here, it should really be the beta E2, because the E2 reaction is a beta. The E stands for elimination. And once again, the 2 stands for bimolecular. So let's break it down and understand what the heck is going on here. First, what is beta? Beta is the second carbon over. So if we start with a molecule that looks like the one we had before, with the bromine, we already said that the carbon holding the leaving group is the alpha carbon. The carbon next to it after alpha comes beta, and so in either direction, even if they're different, that next carbon is called the beta carbon. Beta elimination means that we take something off the beta carbon. Bimolecular, 2 molecules happening at this or reacting at the same time. That means, once again, it's a one-step reaction. Did I put that in the summary? One step is really important. One step right here. And actually, let me put something else here. A lot of times students will try to give me a carbocation on an SN2. Absolutely no carbocation for an SN2 reaction because it's one step. Carbocation is an intermediate step, but we have no intermediate. All right, so the beta elimination reaction is going to look something like this. We have a strong base. We'll use NaOH again in this case, but we'll put it into its own conjugated solvent. In this case, the conjugate acid of an OH- is H2O. Na plus is a positive spectator. The OH- here is negative. It's strong. The solvent, you'll notice, is very polar and protic. It's a polar protic solvent, and that means the solvent is able to do hydrogen bonding. The trick to remember your polar protic solvents is that, just like you and me and my kiddo, hydrogen likes to have fun. And that is, if hydrogen is on F, O, or N, it can hydrogen bond. And so if we look at what we have with the solvent molecule, hydrogen is on one of the atoms of fun. Now you're not going to see F in this chapter, no fluorine reacting in this case. So we're just looking at oxygen or nitrogen. The polar product solvent is going to disrupt a nucleophile by surrounding it with partial charge and making it less reactive. But a base, if it gets surrounded by a hydrogen, is just going to take a hydrogen, which will make another base, which will take a hydrogen until eventually it reaches the molecule. That is why E2 reactions, the polar product solvent will favor E2, but the A product will favor SN2. Instead of attacking the molecule directly, the OH minus, in this case acting as a base, is going to look for a nearby hydrogen. So we have two hydrogens here. Three hydrogens there, I can count, and two hydrogens here. The OH minus is going to grab one of those hydrogen atoms, and when it does so, hydrogen is going to form a bond to the oxygen. But that puts way too many bonds on hydrogen, and so this bond here is going to break. Where is it going to break? Well, we already saw that the electron density is being pulled in this direction. The alpha carbon is feeling partially positive because bromine is pulling the electrons away from it. And so that is where the hydrogen's electrons will be attracted. That will ultimately kick out the bromine, giving me a product that looks like this. And this is not the only product I can get, but this is the first one I'm showing you, where these are my light green electrons. Off in solution, I have the OH now sitting with an extra hydrogen on it. I formed water. Off in solution, I also have a Br minus. Now with these electrons, let's give them a color so we can see. Now with these electrons, and we don't really care about it, it's a conjugate base. In one step, I got my product. That is the alkene, and that is a simple one-step E2 reaction. But that's not the only product we could have gotten. So let's take a look. If I have a starting molecule that looks like this, we already saw what happened when we grabbed one of the green hydrogens like this. But don't forget, this molecule can rotate 180 degrees. It can rotate 360, but I'm going to show you specifically the 180. That means if we keep this exactly as it is, and then now we bring it, well, we don't want to do a 180. We want to do some other bond angle because I want to show what happens when I have when I have this right here, and then one of the green hydrogens over here, and then over here like that. In this case, if I have the OH minus come in, grab the hydrogen, collapse the electrons, kick out bromine, my product is going to look a bit different, even though I grabbed the hydrogen off the same exact carbon. Look at that. For the first one, I gave you a trans alkene for the product. For the second one, I gave you a cis alkene for the product. Which is the major product in this case? Which one do I prefer? Knowing that, in fact, that is still not all that I can get. I could do one more. Because another option is, and let's change the color here. Let's put it in light blue. If I grab one of the hydrogens off the end, I can have yet another product forming that looks like this. Right there. So this one right here is not cis or trans because it's on the end of the molecule, but this is less substituted. So I want you to think about it and let me know in the comments, if you're watching the recording, still let me know in the comments, which of these three products is going to be the most stable, which of these three is going to be the least stable, and why do you think that's the case? So we had a trans alkene. I think I had it in green. We have a cis alkene, also in green. And then we have a terminal alkene, which I gave you in a light blue color, like that. Okay. So there's two things you want to look at when you're trying to figure out the stability. We're looking at the degree of substitution and then how the groups are oriented with respect to each other. For the first one, notice that this is a di-substituted pi bond, and this is also a di-substituted pi bond. This is mono-substituted. How did I know? Use the highlighter trick. Just take a highlighter, highlight the pi bond, highlight the pi bond, and then see how many lines come out of the pi bond to carbon. 1, 2, 1, 2, only 1. That's why the last one is mono-substituted. When it comes to pi bond stability, the greater the number of substituents is going to give you a more stable pi bond. And so in this case, the more substituted are going to be more stable. This is the least stable. And because it's the least stable, it's least likely to form, making it the minor product. These two have the same degree of substitution, and so you also want to look at any potential steric hindrance. When you have a cis alkene, the groups are very, very close to each other. Trans, they're far away from each other. When they're so close, there's some steric hindrance here. It's not happy. That means that the most stable is your most substituted alkene, and specifically the trans alkene, making this right here the major product. Whose rule is this? Meaning this being the major product follows someone's rule. And what is that rule all about? Let's keep the comments relevant to today's topic specifically. And Danny is asking, is the tertiary most stable? In this case, we only have di-substituted, and mono-substituted, but you bring up a very good question. So let's write out all the different types of pi bonds that we can have. This one right here is tetra-substituted. Notice that if I highlight the pi bond, I have tetra, 4 groups coming out of it, 1, 2, 3, 4. This would make the most stable pi bond because it's the most substituted. The next one that I can have is tri-substituted. This one's got 3 groups coming out of it. Again, highlight the pi bond. Notice that you have 1, 2, and 3. Tri-substituted. For di-substituted, we could have 3 different types. The most stable is the trans. The second most stable is cis. And the least stable of the di-substituted is when they come out of the same carbon. Notice that in each case, I have the pi bond that I'm highlighting, and there's 2 bonds to carbon coming out of that pi bond. But this one is the most stable. Less stable than that is the mono-substituted pi bond. And less stable than that would be just a no-substituted pi bond, which I kind of just threw up into the corner because we ran out of space. This is di-substituted, but luckily we're not dealing with paper, so I can actually move this over. Look at that. We ran back into space. So this one right here is mono-sub. And this one right here is not substituted. That makes it the least stable. The rule that you want to follow in terms of figuring out the stability, that is Zaitsev's rule. Zaitsev's rule says that because the more substituted pi bond is more stable, you want to form the E2 reaction is going to prefer the more substituted pi bond rather than the less substituted pi bond. So let's go back then to our molecule here. One way to figure out the product or to figure out the more stable product is to draw out all of them and then look to see which one is more stable. Let me know in the comments. Let me see hearts in the comments if you want a faster way to just look at your starting molecule and immediately know, oh, this is my one most substituted product, most stable product without having to draw the rest. So give me hearts in the comments. Here is a trick to come up with the most stable product. We'll use the same molecule that we had before. But this time, instead of coming up with a product right away, I want to look at my beta carbons. This beta carbon here, it has 2 hydrogens. The hydrogens are di-substituted, but I don't even have to look at the hydrogens. I can just look at the carbon, and I say this beta carbon is secondary. Then I look over and I see this right here and I say this beta carbon is primary. And here is the trick. The more substituted the beta carbon has more substituted hydrogen, which will give you the most substituted product. So to get the most substituted product, the first thing you want to do is one, find the most substituted beta carbon that has hydrogen. If it doesn't have hydrogen, obviously it doesn't work. And two, you want to draw the skeleton, the molecule that you started with, and a pi from your alpha to beta. So what does that look like? All I do is look at my starting molecule. I redraw the skeleton. And then, because this is my alpha and my more substituted beta, I just draw a pi bond from alpha to where I had the more substituted beta. And that's it. That's my most stable, most substituted product without having to look at anything else because I'm good to go. So this is called my Zaitsev product. Or if your professor asks it in a different form, this is your major product. Now, earlier when I was showing you the E2 reaction and rotating the molecule, did you notice how I was particular with making sure I grabbed the hydrogen that had the dashes? The reason for that is when we look at this reaction, let's look at the mechanism from the side. If I have a bromine here and a hydrogen here, and I'm going to eliminate it, the base comes in, and even though you don't have to understand the orbital chemistry at the organic chemistry level, I'm going to explain this just simply enough for you to follow this reaction. The way that these orbitals are oriented, when the oxygen grabs the hydrogen lets go of its electrons, and like dominoes, these electrons will collapse. Like the orbital will fall into the orbital here, which will fall into the orbital here. And the only way to carry out this elimination is to have all the electrons follow the path of a straight line. So it's a domino effect where they have to be perfectly lined up so that the electrons can fall one into the next, into the next. Do you see how this is perfectly lined up? This idea is that they have to be anti and coplanar. So many professors will teach anti-coplanar but will not explain it. They have to be perfectly lined up. If I draw this in a Newman projection, it'll look something like this. Well, we have, I'll just put the other hydrogens in gray so that the Newman projection will make sense. We have in the front, we're looking at it from over here, so that's the eye, that's the eyeball. You have the two hydrogens that are gray going up, the green hydrogen going down. Then this carbon is sitting right there behind it. Let's also give this one two lighter gray hydrogens. So that means hydrogen here, hydrogen here. I don't know why I'm not giving myself more space. It's not like I'm wasting paper. And then what I have in the back is that bromine here. Do you see how they are perfectly lined up? My hydrogen and my leaving group have to be perfectly lined up. So you have to line up your H and your leaving group. Let me know if this makes sense, because this will help with when you have to come up with some of the trickier molecules. For example, let's say professors love to give rings. Let me know in the comments if your professor likes to intentionally put everything on a cyclic structure just to scare you on purpose. Okay, so let's say I have a CH3 right there, and I have a bromine right here, and an ethyl group right here. In a situation like this, if I want to figure out which hydrogen to grab, no, I want this one on dashes. If I want to figure out which hydrogen to grab, I can either grab the green one that is going to the back, or I can grab the light blue one that is coming out of the page. The trick for figuring out the most substituted was to look at your beta carbon and to see which one is more substituted to give you the more substituted pi bond. Well, this one right here is tertiary. This one right here is tertiary. They're both equally substituted, but I can't simply grab either hydrogen for two different products, one of the hydrogens will be impossible to eliminate. Can you see which one? And more importantly, can you see why it's going to be hard to eliminate? If I draw this in a chair conformation, okay, let's see. Dania is saying that makes more sense and it works. Let me show you this trick and you'll see how much faster this is going to be. If I draw this in a chair conformation, remember that I told you hydrogen and leaving group must be lined up? Well, in this case, let's make this carbon number 1 and we'll go clockwise. And I only care about numbering the 3 that are relevant. On carbon 1, I have a methyl group on a wedge, which is the up position, in this case axial. That puts the hydrogen down equatorial. On carbon 2, I have a bromine down, which happens to be axial. I don't care about the hydrogen next to it. On carbon 3, I have an ethyl group down, which makes it equatorial. And that makes the hydrogen over here axial. Remember I told you that the electrons and the orbitals and therefore the atoms have to be lined up? If I want to eliminate this one right here, if I come in with a base and grab it, the electrons have to make a U-turn. They go from this, they don't just collapse that way, they have to collapse in this direction. It's not a straight line. That means I absolutely cannot eliminate the light green hydrogen because it is not anticoplanar. It's not anticoplanar. Cannot eliminate. But if you want to grab the light blue one instead, bring the base, grab it, collapse it, collapse it. Do you see how it goes perfectly in order? The orbitals will perfectly collapse. So only this one is the one I can grab. So one way to figure out which one is the correct one to grab is to do exactly what I just did here, excuse me. And that is to draw it out in a chair conformation. And this is the correct way to do it. This is how your professors do it. But give me a yes in the comments if you want a faster way, because on your final exam, you don't have time to draw chair conformations every time your professor decides to do a ring. Here is what you're going to do instead. In recognizing that the hydrogen and the leaving group have to be anticoplanar, looking at it on a chair conformation, I want you to recognize very simply that hydrogen and leaving group must be axial so that they can be lined up, which is great if we draw it in a chair. But more importantly, they must be trans. If hydrogen and bromine are in opposite directions, then I can put them transaxial and I can eliminate. The key is transaxial, which means I don't need any of that to figure it out. All I have to do is look at my starting molecule and ask myself, which hydrogen is trans to bromine? If bromine is down and this hydrogen is down, that's no good. The green hydrogen is cis to the leaving group. The blue hydrogen is trans to the leaving group. That is the one I grab, and I don't have to worry about the chair conformation whatsoever. What do you think? Just saved you 30 seconds on your exam, 45 if you're not very quick at drawing the chair. All right, so let's go back to, I just want to see if I gave you that yet. No. So let's take a look at it right now. So let's take a few tips for the E2 reaction as follows. For an E2 reaction, okay, so first of all, the rate, which we haven't looked at yet, the rate of an E2 reaction is equal to some constant K. Because it's a 2, we need to have two things in parentheses. The first one is the alkyl chain, the molecule holding the leaving group. And the second one is the attacker, which is a base. And that is how we get the 2 in E2. Because it's an E2 reaction, meaning a 2-type reaction, there will be no carbocation. No car. I hear screaming in the background. I don't know if you can hear it, but I don't know what my kiddo is doing. Don't worry, my husband's with him. No carbocation. And then that means this is a one-step reaction. We require a strong base. We're going to favor the more substituted pi bond. So Zaitsev's rule applies. Zaitsev's rule means you grab the most substituted hydrogen. I'm trying to think if there's anything else to add here, because I know that students like to have a quick list to refer back to after. And it can happen in primary, secondary, tertiary. This is all possible as long as you have a beta hydrogen, because sometimes you don't have a beta hydrogen. There's one exception to Zaitsev's rule, and that is when we're dealing with a triple B. Triple B stands for what? Big, bulky base. If you have a really big, really bulky base, the reaction is going to change. How is the reaction going to change? Let me know in the comments if you know. Actually, I see a couple more students have joined since we started. So if you came late, let me know in the comments, where are you tuning in from? And when are you testing? Are you taking a final exam? Are you taking another exam? Just let me know in the comments so I get an idea of who we have here and what you're studying for. A big bulky base would be something like tert butoxide. Professors will write it in many different ways, intentionally to confuse you. But something like this, it stands for tert butyl oxide. And the K is just the K plus positive spectator. A tert butoxide looks something like this. And I'm intentionally going to draw all of it out, because if you can see exactly what is going on here, you will understand why it behaves the way it does. I want you to notice just how big and bulky it is. And yeah, there's a reactive oxygen right there. But look how much bulk is going on this molecule. Look how much is around it. If I try to take this molecule and grab a hydrogen, so this is the same molecule we've looked at before, and try to grab this hydrogen, it's too sterically hindered. The big bulky base is going to look for the easiest to grab hydrogen somewhere on the side of the molecule where it can reach. So imagine trying to walk into a doorway with a massive umbrella. That's what this is, a massive umbrella. You can't get in the door. You're just going to stick your hand in and grab whatever the person is trying to pass to you. And so the big bulky base is not going to follow Zaitsev's rule. It'll give you the Hofmann product instead. And the Hofmann product is your less substituted pi bond. So if we look back at what we had before, and I give you this right here, that was the Zaitsev product, that would be the product if we use the big bulky base, because that is the only thing that we can grab when you have such a big bulky base going on. All right, let's see. Tucker is watching at work. I like that. For an Oreo 2 exam on Wednesday. And Yoram from Zambia, finals in July. Wow, you have late final exams, but hey, that means you have more time to study. All right, so that takes care of our E2 reaction. Now we're going to switch gears and look at a completely different type, starting with SN1. The SN1 reaction, once again, stands for substitution, nucleophilic, but the 1 is different. We haven't seen the 1 before. Substitution, nucleophilic. The 1 stands for unimolecular. And unimolecular does not mean one step. This is going to be a many step reaction, sometimes 2 to 3, maybe more, but typically 2 to 3. This means we have one molecule at a time. One at a time. That means it's a multi-step reaction, and that means it is a very slow reaction. Let's see what that looks like. If I have the same starting molecule as before, with bromine as a leaving group, but this time I react it with water, just H2O. If I don't have a strong nucleophile that wants to come in and attack, then nothing is here to kick out the bromine atom. And so the bromine, being very partially negative, as we already saw, is pulling on the electron density and pulling and pulling and pulling until finally it just breaks off. The amount of time it takes to break off is a really, really, really long time. And that makes this a very, very slow step. This right here is the carbocation. And the carbocation formation is very, very, very slow. This is the rate determining step of the reaction. Everything else is going to happen really quickly as a result. Water is my solvent, but I don't have anything else here. I don't have another molecule to come and attack. And so even though water is neutral and it doesn't have a charge and it's not very strong, when the oxygen senses that there is a carbocation, the electronegative electrons on oxygen will reach out and take the opportunity to attack something positive, giving me what is still not my final product, because what I have now is an oxygen, 2 hydrogens, 1 lone pair, and a positive charge. We don't like to have charge on the molecule. That does not make it stable. And so we have to wait and wait and wait until something else in solution. Well, how about another water molecule, because I have millions and millions, comes and grabs the hydrogen, gives oxygen back the electrons, and that will give me something that looks like this. Oxygen now has just 1 hydrogen, 2 lone pairs, no charge. Somewhere in solution, I have a hydronium with that extra hydrogen that it grabbed from the blue oxygen, lone pair, positive charge. Which brings up a very good question. What kind of reaction is it if it reacts with H2O and H+? Sometimes you'll be given the reaction like this, and sometimes you'll be given H2SO4 as your catalyst. H2SO4 is not an attacker, it's an acid catalyst. And because it's such a strong acid, it immediately dissociates to give you an H plus in solution. And so it's not the H2SO4 we care about, it's the H plus. That is just there to make the solution more positive, to promote the idea of a carbocation or a hydronium or just positive forming in solution. And when we have positives in solution, they get picked up by water. So the water can attack the carbocation, the water can attack a hydrogen, the water can attack the acid catalyst. Whatever the case is, we're going to have a lot of hydronium in solution, and this just makes it an acid catalyst. So Dania, that was a really good question. I hope that was clear. When you don't have an attacker explicitly given, and the solvent is what ultimately does the attack, this is considered a solvolysis reaction. Solvolysis, the solvent breaks. That's when the solvent is also the attacker. And that is very, very common to see in your SN1 and your E1 reactions. All right, so that is the basic mechanism of the SN1 reaction. And I want you to notice how we started with a chiral carbon, and I drew the product with just a line. But is this a chiral molecule, my final product? Well, yes, it is, because this carbon has oxygen, ethyl, methyl, and an invisible hydrogen. So really, I should have drawn this product chiral. Would I have drawn it correctly if I put the OH on a wedge, given that my starting molecule was on a wedge? Or would I have drawn it correctly if I did an inversion, just like with SN2 reactions, and put the OH on dashes? The answer is, well, both. Because I have a carbocation intermediate. The intermediate, what is the hybridization of a carbocation? It's sp2 hybridized. And if you remember, something that is sp2 hybridized. So we have an sp2 intermediate. That means it's trigonal planar. Another way to say trigonal planar that is easier to understand is the fact that it's flat. The carbocation can get attacked from the top and the bottom, and that means we're going to have both. So you have two products in about a 50-50 ratio for the most part. Sometimes something will make it go a little bit more in one direction or the other, but you're going to get a racemic product if it's chiral, given that we had the carbocation intermediate. I told you that the carbocation was a really, really slow step, and that means the rate of an SN1 reaction is going to equal to some constant K times just the alkyl halide, because as soon as the carbocation forms, it immediately is going to finish with a final step, and that's it. So what do we need to know and recognize for an SN1 reaction? We have the rate. The clue is that we have a carbocation intermediate. And because we have a carbocation intermediate, the more substituted the carbocation is going to be more stable, which means it's also going to be the faster reaction, because if the carbocation formation is the rate determining step, the faster it forms, the faster your reaction. So let's take a look at what makes a carbocation stable. The idea with a carbocation being stabilized by nearby groups is carbon is considered an electron donating group. It gets electron density from nearby carbons, and I like to think of that as moral support. The more carbons that surround a carbocation, the more stable it's going to be. And so if I have a carbocation that is just a CH3 with nothing else, it's very, very, very unstable. But if I take the carbocation and I put it on a molecule, in this case primary, it has a carbon attached to it, use the pencil trick to figure out your degree of substitution. If I put my pencil down on the carbocation, notice I have one line coming out of it. That is what makes this a primary carbocation. The primary carbocation is more stable, but way, way, way more stable than that is if I move the carbocation over to the secondary position. Way more, or even more stable than that, is if I put the carbocation on a tertiary position. And what is even more stable than a tertiary carbocation? Let me know in the comments. If you're not sure, just put IDKY, which stands for I don't know yet, but I'm about to learn. Even more stable than tertiary would be if I have resonance, but specifically, we can't have a quaternary carbocation. So let's look at this really, really quick. The idea with a carbocation is if I have a carbon with hydrogen, an R group, and an R group, a quick formal charge, and I teach the formal charge shortcut in, let me make a note real quick. Formal charge, okay. By the time you're watching the recording, the formal charge video will be linked in the description. The formal charge shortcut is should minus has. Carbon should have a total of 4 electrons around it. Directly attached, we only have 3. 1, 2, 3. That means it's got a charge of +1. But if I have a quaternary carbon, so for example, something that looks like this. These are all carbons attached to it. You know what? Let's actually draw it out so we can see what's going on. Carbon, R group, no, not hydrogen. Yeah, I guess it could be hydrogen because this time I'm just looking for the carbocation. Should have 4. Directly attached 4, it's got a formal charge of 0. That means there is no carbocation here because it has 4 bonds. If I have 3 rather than 4 bonds, then we have an empty orbital. So what I didn't show you here is that I have an empty orbital, and that is where the carbocation resides. A positive charge means it's hungry. It's a carbocation, it's missing something. More stable than just a regular alkyl chain is if I could have more than moral support. If you have somebody cheering you on, they're helping you. But what if they're actually helping you? So we'll use a very simple example. You're carrying groceries, and I don't know, say your friend just got injured and they're on crutches. They can't lift anything. So you're not going to make your friend on crutches carry your groceries, but they can be walking alongside it and you saying, hey, you can do this. You're so strong. You're carrying everything. I'm thinking of my toddler. He loves to bring in the groceries. So I'll give him a really light bag that has like some vegetables in it. And he's so proud of himself. Meanwhile, I'm carrying like bags of just all the heavy things. And he's got his little bag. I'm so strong. I helping put away the groceries. He loves doing that. More than moral support, though, you know who's more helpful than my toddler carrying one bag? My husband coming to grab half of the bags because he is also very strong. And that is resonance. If I have an allylic carbocation, meaning a carbon, a positive charge right there, but I have the ability to resonate this pi bond, that's more stable. Now, this is a primary and primary, but if I then increase the substitution, so for example, I still give you the same resonance, but now the carbocation is on a secondary allylic, or I put it on a tertiary allylic. And you could do this different ways. For example, tertiary allylic can also be if I have the tertiary like that, where if I resonate, then it goes on to the tertiary. So these are just different options. And what is even more stable than an allylic carbocation? A benzylic carbocation, where you can actually resonate into a benzene ring. So for example, the most substituted carbocation that you can have is this one right here. It's tertiary, and it can resonate into the benzyl group. That is most substituted. I see part in the question, but I don't see a question. So go ahead and type in your question. All right, so looking back at the SN1 reaction, this is what I meant by the more substituted, the more stable, the faster it's going to be. You'll typically see solvolysis, and solvolysis is typically going to be with a polar protic solvent. So the polar protic solvent is going to help stabilize your carbocation, and that is why it's something that you want to look into. Solvolysis or a weak nucleophile, because if it's strong, it's not going to wait around for a carbocation. It's going to do a direct attack right away. It's not going to wait. And a weak nucleophile is typically going to be something that is neutral. Which brings up a very good question from Dania. When you say, I know, I probably should know, no, that is why you ask. You're here to learn. You're here to ask questions. So the question is, what is the difference between a nucleophile or a base? This is a very, very common question. So let me know in the comments, and even if you're watching the recording, let me know in the comments. If nucleophile versus base is your biggest question because you're worried that if you don't know the difference between a nucleophile or base, how are you going to know the difference between a substitution elimination reaction? This is one of the most common questions that I get. The first thing I'm going to tell you is that it does not actually matter. It doesn't matter if something is a nucleophile or a base because you're going to look at other parts of the reaction to figure out what is going to take place. And the reason I say that is because I can give you a molecule like OH minus. Is OH minus considered a nucleophile or is it a base? Well, that is a very good question. If you're thinking nucleophile, you're absolutely correct. If you're thinking base, you're also absolutely correct. That is the problem between trying to differentiate nucleophile versus base. Before I explain the science behind it, here's how I like to think of it. To my husband, I am a wife. To my son, I am a mother. Does that mean I'm a mother or a wife? Well, actually, I'm both. It just depends on the context of the situation. So I'll show this to you with a two-type reaction to better explain what's going on. If I have my starting molecule, as we saw before, with bromine as a leaving group, and we also have the most substituted hydrogens right there on the beta carbon. If I take the OH minus and I grab a hydrogen, OH minus grabs a hydrogen, collapses the electrons, kicks it out, This is OH minus acting as a base. Base grabs hydrogen. If instead my OH minus chooses to attack at the carbon holding the leaving group, meaning the alpha carbon, and kick out the bromine, now it's acting as a nucleophile. That is why we don't care about this question. Now, there are some situations where the molecule will only act as a nucleophile or only act as a base, but really it's about understanding what else is going on. Both of these reactions are perfectly viable. The difference is what else is going on that helps drive the reaction in favor of the SN2 or drive it in favor of E2. In this case, it would act as a base if I put it into a polar protic solvent, because it does not like nucleophiles, and it would act as a nucleophile if I put it into a polar aprotic solvent, because the polar aprotic solvent is going to favor the SN2 over the E2 reaction, and the protic will favor E2 over SN2 if it's a 2-type reaction, meaning if it's not going SN1 or E1, which is also possible, but not with an OH minus. Dania, that was a really good question. I hope that clarified. Question: which one is more nucleophilic or basic between methoxide and ethanoate? So what you want to look at when trying to decide which is stronger is rank it based on how you learn to rank your acids and bases. So let's take it as one question. Which is a stronger base? You have the ethoxide versus the ethanoate. Notice that they are pretty much exactly the same. This part of the molecule is exactly the same. The only difference is this one has the extra carbonyl. So what does that do for it? If you go back to the acid base live stream that I did, we actually did this exact example. Here, oxygen carries the charge all by itself. And here, the oxygen shares the charge. Notice that it can resonate. And because it can resonate, it's going to carry less of a burden of charge, and that makes it less basic. Because it carries the charge all by itself, this one is more basic. That was a really good question. Are all Lewis bases nucleophiles? Not necessarily. There are some bases that will not act as nucleophiles. It depends on the specific situation and it depends on the molecule. Question: are there many bases that can't act as nucleophiles or nucleophiles that can't act as bases? That's a really, really good question. And I can't answer for everything, but I'll give you a couple of examples. Examples of a base that is not going to be, we'll call it bad nucleophile because sometimes it can be a nucleophile, is going to be the triple B. If something is a big bulky base, it's not able to get into the carbon to attack, and that makes it a weak nucleophile. Not that it's a weak nucleophile inherently, it's just too bulky and therefore can't reach. The two examples that you would have learned would be tert butoxide and LDA, lithium diisopropylamine. And the ones that are good nucleophiles and weak bases, I kind of hinted at before. This is when a molecule is polarizable. That means it can hold the charge very well, making it a weak base, but if you polarize it, it can concentrate the charge. So examples would be halogens. Halogens, as you know, are very weak bases, but they're decent nucleophiles, or molecules with resonance. So something like this is not a good base, but it is a decent nucleophile. I-, terrible base, pretty good nucleophile. And then if we're talking about strong versus weak, that I'm really just looking for charge. If it has a charge, it's very unhappy. Charge is a burden. That makes it strong. If it doesn't have a charge, that means it's not looking to attack. And if it's not looking to attack, it's not a strong attacker. That means it's weak. And the way I think of this is, imagine somebody who's very angry. If they're in a temper, they're more likely to do something like hit a wall. But if you're in a very happy mood, you're less likely to hit a wall because you don't have a temper. You're not looking to attack. So if something is unhappy, it's strong, it wants to attack. If it's happy, it's neutral, it's stable, it doesn't want to attack. Before I go into E1, do you want to see, because I completely forgot to show this to you, do you want to learn shortcuts to quickly find all your products without having to draw out your reaction mechanism? Because a lot of professors will give you an exam where you have a question and maybe they'll give you a product, maybe a reactant. If you don't have the time to draw it out, here is how you're going to identify your product. For an SN2 reaction, this is pretty easy. Emma says, I sprinted back to my computer to say yes. Emma, just for you and everyone else who said yes, let's do this. For an SN2 reaction, if you have, we'll start with what we had and then we'll do some practice after. If you have your starting molecule like this, and we reacted it earlier with NaOH, here's how you identify the product. You cross out your leaving group, you cross out your spectator ion, and you just replace your leaving group with that right there. When it's an SN2, make sure you invert the chirality, and there is your product. If, on the other hand, you were given a product and asked to come up with a reactant, let's see how to reverse it, and let's go with something your professors are more likely to give you. Say you have a starting molecule that looks, or a final product that looks like this, and you have N3, and it doesn't matter what it is. In order to come up with a reactant, all you do, and I'll put a box around it so you know which one was the unknown. All you do is, well, let's put a box here so we know where to put our reactant. Cross out your leaving group. You redraw your skeleton exactly as you see it. And then, because I have dashes, if it's chiral, make sure to draw a wedge and give it a leaving group. In this case, bromine, because why not? That covers SN2. What if we have SN1? For SN1, it's a little bit different. If I have my same starting molecule, and I'm told to react it with, let's go with an H plus catalyst and a CH3OH solvolysis reaction, we have to come up with a product. Here's how you do it. You cross out your leaving group. Emma, let me know if this was worth sprinting back to your computer. You redraw your skeleton exactly as you see it. The molecule will still be chiral, but it's going to be racemic. So you can draw it in a squiggly or you can draw two isomers, however your professor wants to draw it. A lot of professors will just do a squiggly to show that it's one and the other. And then you find your attacker, which is typically solvolysis. You take one hydrogen off of the solvent and you attach the rest. OCH3. Boom. That is your product. And it's racemic, so let's just make sure to write that. Let's say you have an SN1 reaction, but for this one, you're given the product and asked to come up with a reactant. So let's make this look a bit scary. Okay, so you were told that this was an SN1 reaction where you have I guess this would be a chiral, so it doesn't matter how I draw it, and you have an OH. To figure out what you had, first, let's put a box so we know what we're trying to come up with. First, whoops, I missed. Let's try to make that a proper box. Okay. First, you redraw your skeleton exactly as you see it. You cross out the group that looks like it was the incoming nucleophile. And then you just put a leaving group on there. Boom. If you also have to come up with a reagent, take your leaving group that you had, that's an O and an H, and just add an H back to it. There you go. Question. Is H plus there just as a catalyst? Yes. So let's say you're asked for the reactant here. Let me actually show you how to do that. Grab whatever group looks like it was the nucleophile, and then just put something like an Na before it so you have the positive spectator. Emma, somehow I knew that you were not available and asked about tricks right then, but hopefully your keyboard is fine and that was worth it. Question. SN1, SN2, which of these reactions has a formation of a carbocation as the transition state? So this is what we talked about before. I don't know if you joined us late, but if you did, make sure to watch the recording, which is automatically going to go to YouTube. And in fact, if you sign up using the link on the screen, oh, no, didn't mean to press that button. I'm looking for, I lost my button. Oh, there we go. Use the link on the screen or see the link in the description to get a copy of the session notes from today, a bonus substitution elimination worksheet that you can practice, and links to all the past worksheets and session notes so that you can review the different topics that I've covered this semester. Okay, so going back to the comments. Your voice resonates between melody and art. Okay, hopefully that's not in a bad way. Didn't get the last example. Which one, so that I can clarify? And while you type that in, let's look at the shortcut for elimination reactions. If I have, again, we'll just take this one right here because this is an easy one to draw all the different reactions. And I want to come up with a product for an E2 reaction, but specifically I want only the major product. I already showed you the shortcut for this, but we'll do it again. You identify your alpha carbon, get rid of your leaving group, redraw your skeleton exactly as you see it, find the more substituted beta, and put a pi bond between alpha and the more substituted beta. If I have the product and I want to come up with a reactant, this one, I don't want to say it's tricky in that it's harder, but rather that you're going to have a lot of options. So let's say I have something like this with a pi bond here, and I want to come up with my starting molecule and my reagent. So I can take my skeleton, redraw it exactly as I see it, and then this is where I want to pay attention. Because E2 is going to favor the more substituted product, I want to make sure I put the leaving group in a place where I would get most substituted. Now here it doesn't matter because this is the most substituted, but what if I actually change that and put it right here? If I put the pi bond right here, I have the option for my starting molecule of the one I put in the box, but I'm going to do it twice. Technically, I could put a leaving group here or here. If I put the leaving group on one or the other, my product might change. And so the trick is for E2, put the leaving group on the less substituted carbon. I want you to pay attention to why I'm saying that. If I put a leaving group here, then the most substituted product would be the only option to eliminate this beta hydrogen and get a pi bond right there. If I put my leaving group on the more substituted, then my product would not go here because look at my beta hydrogens. This one right here, beta equals primary. This one, beta equals secondary. My more substituted product with this bromine would be right here, which is the wrong answer. Do you see why? To get the most substituted pi bond, I need to have my leaving group on the less substituted carbon. Otherwise, I would have gotten a different product. So I'm going to cross this out, but I'm going to leave it on the screen because I want you to see what would have happened if I did this. This would have given me, with an E2 reaction, E2 major, would have given me a product that looks like this, and this is not what I have. Not the same. I'm actually going to cross the whole thing out so that you can reflect on this a little bit when you're studying. Okay, let me know if that makes sense. Now, Dania, I haven't forgotten your question. I'm going to show it again for the next one. As for the reagents, very simple. Just put an Na. My go-to is just an O with an R group. So you can put anything. You can do NaOH or an R group, for example, NaOCH3, NaOET, just really any OR minus. let's look at, well, we haven't done the E1 reaction yet, but I'm going to show you the shortcut anyway, because if this is a pre-finals review, you probably already know the reaction. We're just going to go through it for review. So let's look at the shortcut real quick. If I'm doing an E1 reaction, then the trick to quickly come up with a product is to remember that we're dealing with a carbocation intermediate, but if I want the major, it's going to be Zaitsev's rule again. And so if I have something like H2O, it doesn't matter. I cross out the leaving group, redraw the skeleton as I see it, and put the pi bond between the more substituted beta and the alpha, which is right here. Whoops. And if I have to do the reverse, where I'm given, let's say I'm given something like this, and I have to come up with the starting molecule. All I have to do is redraw the skeleton and put the leaving group anyway. In this case, it doesn't matter if I put it here or if I put it here, because with a carbocation intermediate, you're going to have carbocation rearrangement, which means if I had the bromine here and I put a carbocation here, it would have rearranged to here anyway. And so my final product would have been what I see. And then for the reagent, for an E1 reaction, I like to just put H2SO4 and heat, because why not? And this implies that it's an H2O. But because I didn't actually go into what Dania was asking, let's go back right here. So Dania, your question is how I got the HOH. In an SN1 reaction, notice that what I add here is really just a molecule with a hydrogen that I wound up taking off. I have the CH3OH, I take off the hydrogen, and then I attach the rest as my nucleophile. And so if I'm trying to undo it, I take this right here and I give it a hydrogen. So when I have the OH and I give it a hydrogen, it's HOH, which is really just H2O. So that was a really good question. Let me know if that clarified it. And then let's move on to the last one, the E1 reaction. Just like E2, this is missing a beta because it's not just E1, it's beta E1, where the E stands for elimination. And the 1 stands for unimolecular. Just like with the SN1 reaction, the unimolecular means that it's multi-step. So what is the 1? 1 molecule at a time. Okay, so let's see what that looks like with something like this. All right, and then if I react this with, I said H2SO4 and heat, what is my base in this case? Dania, you are very, very welcome. What base do I have in a reaction like this? We specifically said that H2SO4 is not just a source of H pluses in solution, but it's an acid catalyst. And an acid catalyst is not a base. Hang on, please. An acid catalyst is not a base. But what we don't have here is a solvent. This is just a catalyst. So anytime you see H2SO4 without a catalyst, make sure that you recognize that this is implied H2O. There is water, but it just hasn't been given. You need to recognize that. And now I found my base. There's my base. But water is neutral. Water is polar protic. Water is weak. And I take questions and comments related to what we're talking about. So any questions at all, go ahead and type it in. Water is not going to do a direct attack. It's going to wait for the carbocation to form. So it's waiting and waiting and waiting. And bromine, being electronegative, is pulling and pulling and pulling. And suddenly it pulls so hard, it completely breaks off, giving me a carbocation in solution. A Br with the lone pairs, including the electrons that it got from breaking that bond. We don't care about it. This is what we care about. Water can attack right there. That is an SN1 reaction. Or and equally in competition with SN1 would be the E1 reaction. I already showed you the trick for the major product is to find the most substituted hydrogen. Water is going to grab the hydrogen, collapse the electrons towards the carbocation, and this right here is the major. We have three products just like with E2, but right now I'm just showing you the major, and that is your product right there. So what do we need to know about an E1 reaction? E1 has a rate, because the carbocation is the slow step, it's going to be some constant K times just the alkyl halide. That's it. It's the carbocation formation. The key intermediate in an E1 reaction is a carbocation. It's a very slow reaction. It follows Zaitsev's rule. And something I didn't show you before in SN1, which we'll add in, is SN1 and E1 are always going to be in competition. That means you're going to have a mixture of both SN1 and E1 happening at the same time. So let's go back and fill it in. Where did I put my list for SN1? Right here. So carbocation, substitution, solvolysis, polar protic, and in competition with the E1 reaction. So you'll often see solvolysis, and that means the solvent is polar protic. And you'll also sometimes see heat. Heat helps favor the elimination because heat will stabilize the transition state to forming a pi bond. All right, now that we have gotten through all of the reactions with easy practice along the way, here is what I propose, and let me know. Would you like to see and work through lots and lots more practice together? The number of comments that I see confirming more practice is the number of questions we'll do. How does that sound? See, I should be careful with questions like that because there's always a delay in the chat. And so now I have to wait until all the comments come in. But we can do them one at a time. So what I want to do with these practice problems is as follows. We're not going to go through the mechanisms because we already did. But instead, I want to focus on the shortcuts because on your final exam, you need to be able to get through them quickly. So I'm seeing quite a few comments having come in. Let's do quite a few practice questions. Don't forget to subscribe and a thumbs up for the video if you're liking this so far. We have been going for, 90 minutes. We can keep going, but show me that you want more practice, and within reason. I'll have to stop at some point and make dinner because my kiddo, when I said 1 minute before, I saw him playing with a stick, so I had to knock on the window and tell my babysitter that he can't play with that stick. All right, so here we go. If I have a molecule that looks like this, and you're told to react it with KCN in DMF. We don't want to go through the entire mechanism. We just want to come up with a product. The question is, how do we approach this and what do we do? If you haven't already, and you're not sure how to choose between SN1, SN2, E1, and E2 reactions, I did an entire separate live stream. Make sure you watch that, but I'm going to pull bits and pieces of what I taught there to go through this. I use a 4-part checklist to help me figure out which reaction it is, and that is looking at the alkyl chain, the attacker, the solvent, and the leaving group. This, rather than a flowchart, is guaranteed going to help me find the answer, and I'll show you how. The alkyl chain helps me figure out which reaction can take place based on the fact, can I have a carbocation? Is it too substituted? What is going on? And I see that I have a secondary leaving group, which doesn't rule anything out. The next thing I'm looking at is my attacker. KCN has a positive spectator, CN minus, and I already told you that when it has pi bonds, it tends to be better as a nucleophile rather than a base, because the pi bond system makes it more polarizable. So I'm leaning towards a two-type reaction, specifically SN2. So if I'm looking between SN1, SN2, E1, and E2, because I have a negative attacker, it is too strong to allow a carbocation to form. And that means I'm going to rule out my SN1 and E1. But the fact that it's polarizable, I'm leaning towards an SN2 reaction. Alkyl chain, attacker. Next, I look at the solvent. The solvent is aprotic, which I already told you favors an SN2 reaction. So that justifies it again. Bromine is my leaving group. It's a good leaving group, so I'm good to go. The shortcut that I told you for the products in SN2 is to simply redraw your skeleton exactly as you see it. Invert your chirality. So if I have a wedge, put it on the dash because it's chiral. And then whatever comes after the spectator ion, you just draw on there. And if it's a benzene ring, don't forget the pi bonds as I just did, because you're probably going to lose points on that. Question. You said there are 3 possible products which can be formed in the E1 reaction example. An SN1 product, an SN2 competition. No. It's 3 different elimination products. So why don't we do an elimination example next so that you can see what we're talking about? Let's say I have a molecule that looks like, let's not make it too complicated for this. So let's go with something that looks like this. Ooh. Yeah, we're going to have fun with this one. Okay. How many elimination products can I get for this one? Let me know in the comments. Let's see if anyone gets this right, because this is a very tricky problem. I don't know, a box is not going to be enough to fit them all. We're going to have to just draw them out down here. And we're going to react this with just CH3OH. That's it. All right, let's see. If I, let's put CH3OH and heat. If I have this right here, the number of products that I can have off the top of my head will be 1, 2, 3, 4, 5, 6. I got 6 products. Let me know if you got anywhere close, and if you didn't, let me know how many you can think of. Okay, let's see. Heat, I told you, helps favor elimination, but we still have some substitution in competition. So the first thing we're going to do is grab the skeleton, and we'll start with the substitution products. For substitution in this case, I can have, okay, so this is another trick that I hadn't shown you before. I'm going to show it to you now. The trick I showed you for substitution is you just cut the hydrogen off, get rid of your leaving group, and wherever you have your leaving group, you put your incoming nucleophile, which would be chiral, and so I'll put it like this, OCH3. Then, yeah, this is the trick I showed you before. But here's the thing. Here's another trick to look out for. The carbocation is going to form right there because we're in a one-type situation. That would be my carbocation. Anytime you form a secondary carbocation near a tertiary carbon, you're going to get a hydride shift, potential for a hydride shift. So this is if I have no shift. But if I do have a hydride shift, then my carbocation would go right here, and then my OCH3 would add right there. This is a very tricky question. I don't think your professors would give something like that. So that is 2 products. Now let's go for elimination. The product for elimination for E1 will be first exactly as I see it, with a pi bond between the alpha carbon and the more substituted beta. So this one right here is tertiary, this one right here is secondary. The more substituted beta gives me a product right there. If I put a pi bond to my less substituted beta, that would give me a pi bond right there. But to the less substituted beta, I could also have cis versus trans. And that means I can have a product that looks like 1, 2, 3, 4. Hang on, let me see what I'm looking at. If I rotate it, my pi bond is there, but then I could have this one like that. Okay, so that would be another product. And then don't forget, if you have a carbocation rearrangement and the carbocation goes right over here, that pi bond we've already seen here, but I can also have a pi bond right there. 1, 2, 3, 4, 5, 6 products. Hans, how is that for a fun, tricky question? Dania, this is probably going to be on the more difficult end of anything you would see. And I wasn't planning to do this, but Hans had a really good question. So I figured why not show you all the different crazy options that you can potentially do. What if I give you a molecule that looks like this? And I ask you to react it with H2SO4 and heat. And I only want the major product. So this is where we have to consider all the reactions. SN1, SN2, E1, and E2. And we have our alkyl chain. We have our attacker, solvent, and leaving group. All right, so we look at our alkyl chain. It's sitting on a tertiary carbon, which would make a very stable carbocation, but we absolutely cannot do an SN2 reaction on a tertiary carbon. Get rid of it. Nothing else really here on the alkyl chain. So let's move on to the attacker. H2SO4 is an acid catalyst. It is not an attacker, but don't forget, if it's not given, water is implied. That means we have H2O. H2O is weak. That means it cannot do a direct attack. It cannot do an SN2 or an E2, so we rule those two out. Then the solvent is polar protic, which will help stabilize carbocation intermediates for SN1 and E1. We're good. We do not have a good leaving group, though. OH minus makes a very, very, very poor leaving group. And so what we do is protonate it. We use the acid catalyst and water. Protonate it like this, you get an OH2 plus. It leaves as a water molecule to give me the carbocation. So that means I make the leaving group leave by bribing it. And then I'm stuck with an SN1 or an E1 reaction. Anytime you have heat, heat is going to favor elimination over substitution. And that means the final major product here will be the most substituted. Oh. There's going to be 2 most substituted products because the substitution is exactly the same. So I hope your professor would allow 2 products because we do have 2 major. 1 and 2. I don't know if you're supposed to know this, but this one is less stable. And the reason for that is to put a pi bond in a 5-membered ring is less stable than a pi bond outside of a ring or in a 6-membered ring. So just as a fun fact, I'll show this to you here. If you have to choose instability between this pi bond and this pi bond, this one is more stable. With that in mind, I don't know if you're supposed to know that, so you would have been okay giving 2 final products, what I just showed you, but I'm going to stick to the more stable one. Llama, step 1, pray for help. Step 2, put in the effort by watching videos, studying, practicing, and making sure that you are prepared for your exam. So absolutely, hope and a prayer is a good starting point. Then you got to take action. Okay, so let's go with somehow, someway, you have to come up with a reactant in a situation where you're given NaOH, H2O, and heat, and your final product looks like this. All right, so the question is, what reaction took place based on the product that I see, and how do I undo it to come up with the reactants? As soon as you notice the fact that you have a pi bond means that it came from an elimination, E1 or E2. I don't yet know. Looking at this, that's a strong nucleophile. I know it was an E2, not an E1 reaction. With an E2 reaction, the first thing you do, and I should have put a question mark because where am I going to draw the molecule? With an E2 reaction, you redraw your skeleton exactly as you see it. And then, where do we put the halogen? We can put it here, or we can put it here. If I put it here, then the molecule is symmetrical. It doesn't matter if I eliminate top or bottom, it will be correct. But if I put my halogen here, my leaving group right there, that is my more stable. It's slightly hindered. I have potential for a side product. So to make sure I have no side products, I'm going to put the halogen right there. For even more practice on substitution and elimination reactions, make sure to grab the bonus worksheet along with a copy of today's session notes by going to layfortsci.com/orgolive.